In this lesson, we're going to conclude our look at the acyl substitution reactions of carboxylic acid derivatives, focusing on acid-catalyzed acyl substitution. All carboxylic acid derivatives can undergo acid-catalyzed acyl substitution. The acid catalyst allows otherwise disfavored reactions to occur, especially those using weak, uncharged nucleophiles. In this general example, we see the green OR prime group displaced by the purple OR double prime group. As drawn, the green OR prime group could represent the OH of a carboxylic acid, the alkoxy group of an ester, or even the carboxylate of an acid anhydride. Keep in mind that the reaction works equally well for other leaving groups. The green oxygen could just as easily have been a nitrogen representing an amide. If we look at the reaction mechanism, we see that the acid promotes the reaction in two ways. Early in the reaction mechanism, protonation serves to increase the electrophilic character of the carbonyl. Later in the mechanism, protonation enables the expulsion of an otherwise poor leaving group. The six-step mechanism follows the same repeating pattern of protonate, do something, deprotonate seen in other acid-catalyzed carbonyl reactions. The first step is the protonation of the carbonyl oxygen. This enhances the electrophilic character of the carbonyl and sets up the do something step, which takes advantage of that electrophilic character. In the second step, the nucleophile attacks the carbonyl carbon and breaks the existing carbon-oxygen pi bond. The third step would of course be deprotonation, in this case deprotonation of the alkoxonium ion to give an uncharged, neutral intermediate. So now we repeat the cycle: protonate, do something, deprotonate. If we peek at the final product, we see that ultimately we need to remove the green oxygen. The next step is the protonation of the green oxygen to form another alkoxonium ion. This sets up the do something step. Protonation of the green oxygen transforms it into a good leaving group. A lone pair on one of the other oxygens forms a pi bond with the adjacent carbon, expelling the leaving group. The final step is deprotonation. In this case, the carbonyl oxygen is deprotonated to give the final product. Let's take a look at a few specific reaction types that demonstrate the importance of acid-catalyzed acyl substitution. The first reaction is the Fischer esterification, the reaction of a carboxylic acid with an alcohol to form an ester under acidic conditions. It's important to recognize that the acid catalyst enables the reaction of a carboxylic acid, the least reactive of all carboxylic acid derivatives. The acid catalyst makes the reaction kinetically feasible. However, equilibrium will be split roughly 50-50 across reactants and products. The Fischer esterification is often pushed forward by exploiting Le Chatelier's principle. For example, removing the water as it's formed drives the equilibrium to the right. Using a large excess of either the alcohol or the carboxylic acid also pushes equilibrium to the right. The next reaction is transesterification, the reaction of an ester with an alcohol to form a different ester under acidic conditions. In this example, we see ethyl acetate reacting with methanol to give methyl acetate and ethanol. Because the reactant and product carbonyls are both esters, we would expect equilibrium to be split roughly 50-50 across products and reactants. Just as we saw with the Fischer esterification, equilibrium can be shifted forward by exploiting Le Chatelier's principle. Removing either product as it forms, or starting with a large excess of one reactant, will shift the equilibrium to the right. The last reaction is acid-catalyzed hydrolysis, the reaction of a carboxylic acid derivative with acidic water to form typically a carboxylic acid. The reaction is typically performed with a large excess of water, pushing equilibrium to the right and favoring product. Nitriles can also undergo acid-catalyzed hydrolysis. The reaction can result in the formation of either an amide or a carboxylic acid. The reaction often favors the formation of the amide, but is sensitive to reaction conditions such as time, temperature, and the amount of water used. If we look at the mechanism, we see that it's almost entirely proton shuffling, and follows a simplified version of the protonate, do something, deprotonate pattern. In the first step, the nitrile nitrogen is protonated. This makes the nitrile more electrophilic and sets up the do something step. In the second step, water acts as a nucleophile and attacks the nitrile carbon, breaking one of the carbon-nitrogen pi bonds. The next step would be deprotonation, specifically deprotonation of the alkoxonium ion to give a neutral, uncharged intermediate. If we peek at the final product, we see the only remaining steps are the protonation of the nitrogen and the deprotonation of the oxygen. Because the intermediate is uncharged and the conditions are acidic, we first protonate. A weak base such as water then removes a proton from the oxygen, pushing electrons towards the electron deficient nitrogen and providing the final product.